Hi, this is lesson 17 in the use of JASP and learning statistics. And today we're talking again about reliability and starting to get into some details of factor analysis. Let's get going. We're going to go and open a data set from the data library under reliability section 13. Data set that we're going to open is a made up data set by Andy Field on anxiety about using SPSS and statistics with items such as statistics make me cry. To start off with, I want to go ahead and get rid of most of these so that we can see what it means to add these in. We'll go ahead and leave the coefficient alpha there. I want to get rid of this reversed scored item to start off with. And the advanced options are kind of there by default and are okay. Andy Field proposes that he has a scale depicting fear of statistics, and with items such as statistics make me cry, standard deviations excite me. That one is reverse coded because it's in the opposite direction. All the other items are in the negative direction, such as I weep openly at the mention of central tendency. I can't sleep for thoughts of eigenvectors, and so forth. And what is clicked by default is the coefficient alpha. I've left that one there. That alpha is 0.605, not very good. I'm going to go ahead and add in alpha omega 0.704, which seems to be adequate. One should always start by looking at the item correlations with the rest of the scale. So if you click on this item, it gives you the correlations showing that item 1 correlates 0.51 with the rest of the scale, the average of all the other items. Item 3 is negatively correlated. Now, that's not good at all, especially given that it's a strong correlation of minus 0.549. The reason for that is that we forgot, we actually did it on purpose, but if you're doing real research, you can often forget when you go to look at your reliabilities to have recoded an item that is going in the opposite direction. What do you do about that? One thing I really like about JASP is it makes it really easy instead of having to actually go through the trouble of coding it in the opposite direction. You can just click on the item that needs to be reverse scaled and it reverses it. And now notice that our reliability has jumped up from the 0.6, 0.7 range to 0.82. And you notice that the item rest correlations show that everything's positive. Let's take that back out for a second here, and let's look at coefficient alpha if the item was dropped. And you notice that the shows that if you dropped item 3, that the coefficient alpha would jump up from 0.605 to 0.8. Of course, that changes when we correctly put item 3 back as a reverse scaled item. And now we're seeing that there's no items that if you drop that will take you above a 0.821. So that's what you want to see, that all your items are contributing positively. They all have nice, strong correlations, and reliability indexes are good. Let's go ahead and also get our split half reliability, and it's coming in really close to these. And let's also go down and get our CFA model fit. And I also want to see these standardized factor loadings. And what I've noticed is those standardized factor loadings don't necessarily come in easily unless I click on that button for PFA, and then I can go back and then they're still there. Okay. So my factor loadings all look fairly consistent. They're approximately equal to one another. Not exactly. You have a 0.46, a lot of these are 0.6, 0.65, but they're not real widely ranging. Widely ranging would be if you had like something that was, one of these was a 0.9, which can happen in factor analysis. One of these was a 0.3. Then you'd have pretty big differences. So coefficient alpha basically assumes what is called tau equivalence. Tau equivalence is the idea that all of the factor loadings are very much equal, or at least approximately equal. Now, these are the standardized loadings, but it will do. It is standardized or not. These loadings do look fairly equal to one another. And so that would suggest that the assumption of tau equivalence, it's not a formal test, I'm guessing, but it would suggest that the assumption of tau equivalence is met. And when that assumption is met, then coefficient alpha should become approximately equal to coefficient omega, and that is what you are seeing. Coefficient omega does not make the same assumption that the loadings have to be equal. It assumes that there should be one factor, a single factor. So this set of measures here is fit indices for a single factor model underlying the coefficient alpha that we're seeing. Now, what you'll notice is that you have a chi-square value of 404 with 20 degrees of freedom, and the p-value for that is fairly highly significant. So this is a new concept that I'm going to bring in here that's a complicated one. The chi-square is a measure of model misfit. So this is suggesting that the model does not fit. The thing of it is that the chi-square test tends to be highly, highly inflated. It gets inflated by the number of participants that you have, and it gets inflated by the complexity of the model. The more measures you have, the higher the chi-square value is going to be. For this reason, most people tend to ignore the chi-square value and the fact that that measure of misfit is significant, and they go to what are called goodness of fit indices. I mentioned this before in another video that the RMSEA is one of the most used measures. And what you typically want is for that RMSEA to be below 0.08. As you start to drift over 0.08, that indicates that the model is not fitting well. So this is starting to drift, but I would say for this type of model, and given the multiple complexities that go into model fit, which is really hard to describe in a short video like this, that this is seeming to be satisfactory. And because we are approximately coming up with good fit for a single model, your coefficient omega is relatively good. So remember, coefficient omega is about whether or not you have a single factor underlying the data. And coefficient alpha is about tau equivalence. Tau comes from the idea of the factor loadings that relate the true score, tau for true score, the true score variance to the measures. And that's done by a factor loading. And are those factor loadings are equal? They often come out to be relatively the same. Let me add in one other point, and that is what's going on with this reverse scale scoring, and how would you mimic that? I'm going to take that out and assume that that wasn't part of the programming for a second. And if that's not part of the programming, what I would need to do in order to fix my alphas is I would need to take out this item 3 and I would need to replace it with a recoded item myself. The way that I would do that is I'd go over to my data, click plus to get a new variable, and I'm going to call it RQ03 for recoded. I'm going to use the R window and create a column. And what I'm going to do is I'm going to say 6 minus Q03 dot scale. Why do 6 minus the variable? So here's my variable, and I have a 2 here. And if I rescale it the opposite direction, that 2 should become a 4. It's a 5-point scale, so 1 should become a 5, 5 should become a 1. If the numbers go from 1 to 5, then go 1 whole number above that to 6, then take 6 minus those numbers and it will flip the scale. Let's see. There we go. And now I have my recoded variable, and it is the flip-flop of the 2. Notice here's a 5 for subject number 4, and it's now a 1. Here's a 1 for subject 11, and it's now a 5. So it's flip-flopped. And that's the way that you would recode that scale, and there is your command. And JASP will allow you to point and click play in order to try to get there. But I'm not going to go into any more detail on that right now. I'm going to close that. There's my variables. Go back over to my analysis. And now I can take that recoded item and stick it over here into variables. They all update, and now they give me the same information that I was obtaining before having rescaled the item myself. And that's another lesson in JASP. And next time, we're going to go deeper into factor analysis. Take care.